global field. So, in other words, K is sitting co-compactly and discretely in a locally compact semi-simple ring, A, which is the ring of Adels of K, and A is just, in fact, reconstructed from the places which are, if you want, the quotient of A by maximal ideals, and it's a restricted product. It's restricted according to the condition that a section, if you want, of this family of local fields belongs to A when, for almost all places, it belongs to the maximal compact subring. All right, so then, as I explained last time, by understanding what is the analog of class field theory for Archimedean places, namely this theory of type 3 factors and so on, one finds out that there is a very natural, very non-trivial space which is assigned to this situation, and that space X is a space of Adel classes, which is a quotient of A by GL1 of K. Okay, where GL1 of K, which is, I will denote often by K star, non-zero element in K, which are acting on A by multiplication. So this is a space of Adel classes. And what I want to show is that, I will write a very precise statement very shortly, that the zeros of L functions, in particular the Riemann zeta function, when you take K equals Q, appear just by looking at the Hilbert space, which is L2 of X. There will be a decoration delta, which eventually will go, L2 delta of X, of square integrable functions on X. And by looking at the co-kernel of the inclusion of that space in the regular representation of the ideal class group, which is CK. So CK is just the quotient of GL1 of A by GL1 of K. And both of these spaces will be acted upon, so both are representations of the ideal class group, representations of CK. You see, I mean, of course, the ideal class group is acting on itself by the left regular representation, but it will act on the space X just by multiplication. So in other words, what I am saying here is extremely simple. I am saying that just by comparing addition and multiplication, you get the zeros of the L functions and of the Riemann zeta function, starting from a global field K. Okay? I will make a very precise statement shortly. Now, how does one get the L2 space for a space which is a quotient? Okay? You see, if you consider the situation where you have, say, a manifold M, and you have the universal cover of that manifold, M tilde, okay, and you want to describe the space of square integrable functions on M, L2 of M, directly on M tilde, without actually working on the quotient. There is indeed a very simple way to do that, and that way is the following. You see, you consider functions now on M tilde, not downstairs, but you will endow them with an inner product that will only reflect what they give by averaging when you push them downstairs. In other words, you see, if you have a function with compact support, f, which belongs to, say, smooth functions with compact support, on the universal cover M tilde, you do get a function downstairs by projection. Namely, you do get a function by f of a point downstairs, f of x, is just equal to the sum of f of y, where the projection of y is equal to x. Okay, just summing the value of the function over a given point here. If you take a point here, it will have several pre-image points. And you can sum the value of the function. This will give you a function downstairs. Okay, but instead of writing this equality, you can simply write down the inner product on functions upstairs that when you complete will give you the Hilbert space of functions downstairs. And that inner product is the following. You see, because it's a universal cover, I can write this sum by working only upstairs and by working with the deck transformations, with the action of the fundamental group on M tilde. And what shall I get? Well, I shall get that if I have a function f, so which belongs to smooth functions upstairs with compact support, Okay, then I can define its L2 norm square by the following formula. It is the integral. And now what I do, I average the function. I take like a Poincaré series for the function. So I take sigma of f of gamma x, okay, where gamma belongs to the fundamental group of the manifold, pi 1. Okay, and then you square only after having taken the average. Okay, and you integrate dx on the quotient. All right. Now, if you take function upstairs and you take the corresponding inner product, and you take the corresponding Hilbert space, which is obtained as usual by separating and completion, okay, what you will get is the corresponding Hilbert space is identical. So the corresponding Hilbert space is in fact identical with L2 of the quotient M. In particular, there is something which happens, which is quite clear in this formula, if you want, which is that if your function f happens to be of the form some function g minus the translate of this function by some group element, okay? Assume that you have a function which is obtained as a difference like this. Then what will happen is that when you make the sum here, you get 0. So in fact, that function belongs to the radical of the inner product, radical of the norm, if you want. And so this function evaporates when you take the corresponding Hilbert space. And it is precisely because of this reason that you are identifying points which lie over the base point, the same point downstairs. Okay? So here we are in the same situation. Of course, it's much more delicate because the action of GL1K on A is ergodic. Okay? It's a very non-trivial action. But nevertheless, we do have the same procedure. So in fact, we shall define the L2 space, L2 delta of x, in exactly that fashion. But there are two subtle points. The first one is that, you see, if you take a local field, so if you would work locally, not for a global field, but for a local field. Now, for a local field, I mean, you have the additive R measure dx, okay, and the additive R measure on the field. And you can compare this additive R measure with the multiplicative R measure. So this is the additive R measure on K, if you want, for a local field K. So you have the additive R measure on K, and you can compare it with the multiplicative R measure d star x, which is the R measure of the multiplicative group, and on K cross, if you want. So, and you have the following equality. You have that dx is equal to absolute value of x times d star x. Okay, of course you can choose normalization on both sides up to a scale, but I mean, when you take that product, it gives you the additive R measure. Now, it's a little bit more subtle when you consider the global situation. In fact, in the global situation, what you have is the following. You see, you have on the ring of Adels, so for Adels, what you have is you have the additive R measure, dx. So dx is the additive R measure. Okay, and you also have the multiplicative R measure for the Edels, which is d star x. So d star x is the R measure on Edels. And Edels, you know, this is just the same thing as what I will call A star and the invertible elements in A. Okay. Now you don't have, you also have the module. The module makes perfectly good sense, but you don't have this equality. What you have is that you have dx equals limit when epsilon goes to 0 of epsilon times x to the 1 plus epsilon times d star x. Okay, so it's a little bit more subtle. Okay. However, what is true is that when you rescale an inner product, you don't change the trace of corresponding operators. And we don't care for a scale factor. Okay. So in fact, I mean, but that's a very important point. Somehow that this scale factor is important, the epsilon which is there. Okay. So that's the first subtle point. The second subtle point, but which eventually will disappear, is that we shall need this delta, this Sobolev exponent delta, in the definition of the space. Okay. So for that, I just have to mention in a few words what happens when you consider the regular representation. But so what is this delta? You see, when you take a group like CK, which is a group of Hidden classes, this group, as I explained last time, is really commensurate to positive real numbers. I mean, if K is a number field, CK, so CK, is in fact equal to a compact group cross R plus star, when K is a number field. Okay, if K is a field of positive characteristics, then it is K cross Z, okay, where K is a compact group. So K is compact here. And that means the following. That means that the only infinity in the group is coming from the infinity in R plus star. Now, if you want to control the growth at infinity, it is very natural to control it by the size of the element of R plus star that you have here, but not the element of R plus star, it's a logarithm. Okay? In other words, the natural weight factor is 1 plus log of absolute of x square to the power delta over 2. Okay, so whenever we shall see this weight factor, which eventually will disappear, you see this weight factor is there simply to control the growth at infinity in the space. The space, right? And the same is true of the space x. It has the same sort of infinity, if you want. And at first, when you begin to work, you can. But as I explained, I mean, this delta was sort of a nuisance. And fortunately, it is gone now. But to understand things at first, you have to keep it. All right, very good. So now let me write down the definition of the norm. Now we have all the preparation for it. So just starting from a global field K, so K global field, then we define the Hilbert space L2 delta of x by the following norm. Okay, so we define a norm on functions. Now, what are these functions? So the function f are elements of the Schwartz space of the Adel. Now, I have to define for you what is the Schwartz space of a locally compact abelian group. Okay? I mean, of course, you all know what is the Schwartz space for the real line. For the real line, the Schwartz space, so here it will be the Brouillard Schwartz space. Okay, so, I mean, that's a standard definition, but let me remind you what it is. So the Brouillard Schwartz space is the following. You see, so you know what it is for R. The Schwartz space for R is the space of functions f such that any derivative f to the n of the function decays faster than any inverse power, you know, than any 1 plus absolute of x to the minus k, or any k, when x goes to infinity. So it's functions which, of course, not only are of rapid decay, this is the definition of rapid decay, but with all derivatives are of rapid decay. Okay? So you know what is Schwartz space for z? For the integers, if you take the integers, there is no question of taking derivatives. So the Schwartz space of the integers is just sequences. Okay, I mean, these will be sequences. And these sequences will just be such that in absolute value, an decays faster than a constant times 1 plus absolute of n to the power minus k for any k. Okay? So, I mean, this is rapid decay for sequences. Now, you know what is Schwartz space for the torus? You see, Schwartz space for the one-dimensional torus, this is just smooth functions on the torus. The reason why it is like that is that when you take Fourier transform, it should correspond exactly to sequences of rapid decay. Okay? Now, the definition of Brouillard, of the Brouillard-Schwartz space, is the following. So you take G to be a locally compact abelian group. Okay, I mean, it's good to do it on that blackboard because that's really a completely standard thing. So if you take a locally compact abelian group, G, the Schwartz space of Brouillard is defined as follows. You consider all the subquotients, then you consider all subgroups G0, and you quotient them by subgroup G1, where G0 is open in subgroup of G. So G0 is an open subgroup of G, and G1 is a compact subgroup. G1 is compact in G, but of course G1 is also contained in G0. Okay, otherwise you couldn't take the quotient. So you consider all subquotients like this, which are of the form z to some power, cross a torus to some power, cross R to some other power, cross a finite group F. Okay? You consider all subquotients which are of this form. Okay? Now, for any such subquotient, you know what is the Schwartz space. Because you just take, you know, their nuclear space, their tensor product is well defined. So you just take the tensor product of the corresponding spaces. Now, what you have, you see, you have functions which are supported by G0, which is an open subgroup. So what you have is a big open subgroup, which is G0. The function is supported there, so you can extend it by 0 elsewhere. Okay? And the function is constant on G1 cosets. But G1 is compact. So the function is pretty much decaying at infinity. And now what you do, you just take the union of these spaces, namely, or in a fancy language, the inductive limit of these spaces. So that's the abstract definition. It's due to Brouwer. It's very old. It's very practical. And in all the examples that you have, it gives you the obvious answer. Okay? So, I mean, this is the notion of what is the Brouwer-Schwarz space. So here, in particular, you can take the Adels. They form an abelian locally compact group. Okay? And you can take the Schwarz space of Adels. So you can take functions which belong to the Schwarz space. They will replace these functions that I was talking about when I was taking the universal cover. Okay? And now I will just define an inner product on these functions. Okay? And this will give me my Hilbert space. So what will be the inner product? Or rather, what will be the norm square? So the norm square, there will be an index delta because I want to keep this weight factor. But as I said, eventually delta will be 0. So this norm square is simply the following. Look, I have to imitate this. Okay, so I have to take some integral. I don't know how we'll take the integral so far. Then what do I have to do? I have to take the sum of the function for the action of the group. The group is GL1 of the field, so it's non-zero element of the field. So it is just sigma of f of qx, okay, where q belongs to k cross, the invertible element in k. I take this sum, I square it, okay, and then I want to integrate it with respect to the additive R measure. Okay, but I have to put the weight factor, which is 1 plus log of absolute of x square to the delta over 2, okay, which eventually will go, as I said, for delta equals 0. Okay, and then what do I put? I just put the additive R measure, but I put it in the guise that it is absolute of x times this times. Okay? Okay, so I just put it in this guise. Fine, so this is a norm square. Now, what you see on this norm square is that you have a little bit of work to do, because it is not true that if you take an arbitrary function in Schwarz space, this integral will be finite. And the reason why it's not true is that you recognize when you take these sums, you recognize the Riemann sums for the integral. And so, in fact, you have to impose two linear conditions on the Schwarz space. So you have to take a subspace of codimension 2 in the Schwarz space, which I will denote by S of A sub 0. And the two conditions are the following. So f belongs to S of A sub 0. What this means is that f of 0 is equal to 0. See, it would be a little bit annoying, but I mean, that wouldn't be serious if the function was not vanishing at 0, because you are taking the sum of f of qx. And of course, if I take x equals 0, qx is equal to 0 for all values of q, and you are just repeating f of 0 infinitely many times. And the second condition is that integral of f dx is equal to 0. Okay, so this is a space, and okay, so the space is just obtained by completion for this inner product. And as I said before, you see, just by the very definition of the inner product, it wipes out the functions which are differences between a function and its translate. So that just this inner product from functional analysis does affect the quotient of dividing the space X by the action of GL1 of K. Now there is another instance in physics. Yes? Sure. What is the short space of? Oh, of periodic numbers. If you apply the definition of Brouwer, let's apply it, okay, for periodic numbers. You see, in periodic numbers, it's totally disconnected, okay? So we certainly cannot have a subquotient which will give us a torus or a line, okay? So in fact, what you find out very quickly is that elements in the short space on periodic numbers, because it's on dual group also. So if you apply to the dual group, you find that you cannot have also a power of z. Otherwise, you would have continuity in the dual group, in the Pontryagin dual group. So what you find out very quickly is that there is no such subquotient except when the subquotient is a finite group. Okay? So in other words, the short space for periodic numbers are just functions which are compactly supported and locally constant. Okay? Now, there are plenty of such functions. And typically, I mean, you know, an example of such function is the characteristic function of the periodic integers, okay, which is the maximal compact subring of the periodic numbers. Okay, but however, what you can see, and I mean, this requires a little thought, is that, for instance, if you take, you know, the product of many periodic numbers for different places, you'll find that there are very few functions which are in the Schwarz space. Okay, but there are enough such functions to separate points. But these functions are the most regular you can imagine. They are compactly supported. and they are locally constant. Okay? But of course, as soon as you have infinite places, then you have many of them. Okay? Okay, if you consider a multiplicative group of periodic numbers, then the situation is slightly different, because in the multiplicative group of periodic numbers, you have the powers of the prime generator, which generates a subgroup which is Z. Okay? So in that case, you do have a factor Z, or dually, when you pass to the dual group, you have a torus. Okay? So in that case, the Schwarz space is not so trivial, in the sense that you have functions, if you want, which are no longer compactly supported, but they have rapid decay. Okay? So I mean, you have to get used to it. This definition is a very, very standard one, sort of. But it's useful because, indeed, we shall meet not only the Schwarz space for the Adels, we shall also meet the Schwarz space for the Liddell class group. Okay? And the definition will be the same. All right, so I mean, we apply this very simple thing, and we get to Hilbert space. Yes, sure.
What is the weighting factor for?
Well, I will explain that. Okay, this is the most important question. And as I said, I mean, the fact that it will disappear, I mean, is very important. But you see, let me explain why I put it in, and how it will disappear. So the reason why I put it in will be sort of obvious if we sort of strip everything from details and look only not at this space, which is a fancy space, but if we only look at the Liddell class group, and in fact we even strip it from all useless details, we strip the Liddell class group from the compact piece, and we just look at L2 of R plus star. Okay, and of course we can think of R plus star using the exponential map. I mean, you know, this is of course by the exponential change of variables, L2 of R. Okay, so what are we doing in L2 of R when instead of using your ordinary inner product in L2 of R, we put a weight factor? Okay? In other words, we replace the norm of a function in L2 of R, which normally is integral of psi of t squared dt. We replace it by integral of psi of t absolute square multiplied by 1 plus t squared to the power delta over 2 times dt. Okay, what happens when we do that? Well, you see, what happens when you do that is that when you look at the regular representation of the real line on itself, okay, by translations, this representation is no longer unitary because of the weight factor. You see, if I take this inner product, okay, and I call that the norm of psi, and I put now a delta square. I mean, it's certainly squared. Now you can consider the regular representation of the real line on itself. Let me call it V of S. So V of S psi, evaluated at the point t, is just psi of t minus s. Okay? Now, this representation is certainly no longer unitary, because if I shift the t by an s, I will pick up a 1 plus s to the power delta over 2. Okay? So, I mean, it will, however, satisfy a very good condition, which is that the norm of V of s doesn't grow faster than a polynomial. Namely, it's a big O, if you want, of t to the power delta over 2. Okay, but what do you gain? So you have lost unitarity. What have you gained? Well, you have gained something which is extremely nice at the start, which is that, you see, when you look at this representation, if you look at the regular representation for delta equals 0, you'll find out that the corresponding infinitesimal generator, okay, is an operator which has purely continuous spectrum. Okay, namely, its spectrum is Lebesgue, and it's purely continuous. When you introduce a weight factor, and provided delta is bigger than 1, what you'll find out is that now it will be a pure point spectrum. In other words, by introducing this weight factor, you have allowed for eigenvalues of the representation, and you can see this, that you get pure point spectrum by dualizing. I mean, if you consider the dual space, you see this is like a Sobolev space. I mean, if you work in Fourier. Okay? And by dualizing, what you see is that the function, which is just the exponential function, I mean, it doesn't belong to that space, but it defines a continuous linear form on that space. And it is actually an eigenvalue. So let me explain the reason why I put it in before. Okay? The reason, as I explained, is that the set of zeros of zeta, or of L functions, will appear as an absorption spectrum. Okay? So, but what is the regular representation? It is white light. Now, if you take white light as it stands without a delta, okay, it is continuous spectrum. And continuous spectrum by quotient can never become an eigenvalue. You see? I mean, it's impossible if you have continuous spectrum that by taking a quotient or whatever operation you'll get eigenvalues, because they would be liftable to eigenvalues in their original space. So the reason for the delta was sort of ad hoc at the beginning, but it was sort of like focusing, you know, like when you want to look at something. So I was focusing by using the delta, in order to see the zeros of zeta and of other L functions. But of course, in the long run, this was bad because it was ad hoc. Okay? And what I will explain is that when you make a cutoff, like in the Zellberg trace formula, you don't have to focus. I mean, you see these zeros appearing already per se, as they are. Okay? So, I mean, this is indeed a very important point. All right, so now let me state the theorem. So you see, what we have Hilbert space, and we have this sort of focusing factor delta. And now we can write down the theorem. So the theorem is the following, is that if we consider the restriction map from L2 delta of x to L2 delta of ck, so what is this restriction map? So the restriction map is given as follows. You see, you take a function f, which belongs to this short space, S of a sub 0, and what you do is you consider the corresponding vector in this Hilbert space. Okay? And now to it you associate the following. You associate to it the following thing, which is E of f, but evaluated only on an ideal j, and which is just sigma of f of qj. Okay, but I want to multiply it by the norm of j to the power 1/2. Okay, and the sum is over q belonging to k star. Okay, and this will be a function. So this is a function on ck. Now, if you look at this function, it's sort of obvious that E is an isometry. When you endow L2 of ck, I mean with the Sobolev norm precisely, namely L2 delta of ck, an element eta here as a norm which is given by the integral of eta of j absolute value square multiplied by 1 plus log of absolute of j square delta over 2 times d star j. Okay. Now what is quite important is this factor j1/2. You see, you have the factor j1/2, and the reason for the factor j1/2 is the fact that when you want that when you raise this to the square, the measures that you get is like the additive R measure. Namely, it is absolute of j times d star j. And this is what forces the j1/2. Now, this j1/2 is the same as the 1/2 of the critical line, okay, for the zeros. So, I mean, the place where the critical line appears, and the reason why you only see zeros on the critical line is precisely this 1/2 here, and the fact that you are dealing with Hilbert spaces, okay? So that's a very important factor, this j1/2. Now, at the level of representations, let's take some notations. And the notation I will use will be the following. So you see, for the action of ck, of the ideal class group, on L2 of x, and including with the delta, will be denoted by u. Okay, so in other words, by u. So what I mean is the following, that I will have an operator which will be u of a, or u of g, acting on a vector psi, function f, if you want, f evaluated at a point a. This will be f of g inverse a. Of course, the ideals act on the adels, but it's a little bit more subtle to realize that this action only depends on the ideal class. Why does it only depend upon the ideal class? Because you can choose various lifts of j as an ideal. But if you change the lift by the remark I was making, that if the function is of the form g minus g gamma 0, it is in the radical of the norm, you don't change the corresponding vector. Okay? So it is quite clear that this action is an action not of the group of ideals, but of the group of ideal classes. Okay, so we do have this action, which I will denote by u, and I will denote by v the regular representation. Okay, I will denote by v the regular representation of the, exactly as I was doing here, the regular representation of the ideal class group on itself, of ck on L2 delta of ck. Okay, and finally I will denote by w, but let me just write it for the statement of the theorem, the quotient action. You see, the map E, the restriction map E, is equivariant in the... Yes? Well, even if you take delta equals 0, the action u is not unitary. I mean, because of the scaling of the additive R measure by the module. Okay? But because I have put in the factor g to the 1/2 here, okay? I mean, this unitarity is restored when you pass to the representation v. Or you need delta equals 0. If delta is not equal to 0, the action is almost unitary in the following sense that I will write down here. Okay, so it's so if delta is not 0, okay, the action is not unitary, but the action satisfies the following: that when you consider v of g, or okay, it could be the same as the others, the norm of v of g is a big O of the log of the norm of g to some power, okay, which is in fact delta, or delta over 2. Okay, and that's, you see, what does this say? This says that the spectrum is unitary, even though the representation is not unitary. Let me explain that little point. It's quite an important point. You see, let me take a representation not of a big group, but of Z. Okay, then I have a single operator. And V of G is the powers of this operator. So V of G is now, you see, like V of N is a certain operator T to the power N. Let me show you that if this condition is true, then the spectrum of the operator T is inside the unit circle. So it's unitary. Sure, but the spectrum is on the circle. Okay? And the reason is the following, is that you just apply the spectral radius formula. So you see the spectral radius formula gives you the following. It gives you that the norm, the spectral radius, spec radius of T is equal to the lim sup of the norm of T to the n to the power 1 over n. But you see that the norm of T to the n grows like a polynomial. So when you take it to the power 1 over n, you get 1. And similarly, this applies to the spectral radius of T inverse. So you get that spectral radius of T is 1, spectral radius of T inverse is 1, so you are done. Okay? And the same applies for any representation. So this is not a big deal. And it tells you that, well, even though you have a price to pay because of the delta, a little bit like in solar space, the price is not too big because you remain like in the unitarity class. Okay? But you allow Jordan box precisely. Okay? I mean, it's not semi-simple any longer. Okay, so now let's write the theorem. We have everything we need. Except I want to write the equivariance of the map E. You see the map E that I have defined, it satisfies the following. Let's compute the equivariance condition for E. So let's compute what happens when you take E of U of G of F, okay, and evaluate this at A. So what is this? I mean, this is equal to the norm of A 1/2 multiplied by the sum of U of G of F evaluated at QA, for Q belongs to K star. Okay, and I mean this is equal to F of G inverse QA. Of course, everything commutes here. I mean, if you are dealing with GL2, you will have to be careful, but everything commutes here. So in fact, what you get is the following. You get G to the 1/2 times J inverse A to the 1/2. So far I have done nothing. You know, I have just written the fact that the normal product is product of the norms. Okay, multiplied by the sum of F of Q G inverse A. Okay, but what is this? That's exactly E of F evaluated on G inverse A, but this is V of G E of F evaluated at A. So what we see is that you see there is a factor of G 1/2, namely this is equal to G to the power 1/2 times V of G times E of F. And this G 1/2 is very important. It is exactly the same when you deal with the L-adic cohomology and the action in H1 as a power Q to the 1/2, which enters when you look at the eigenvalues of the Frobenius, etc. Okay, so this G 1/2 is it's very important that it is round. Okay, this factor. You see, the action, what I am saying is that even if you take delta equals 0, the action of the ideal class group on L2 of X is not unitary. It has a scaling property. And that scaling property has exactly the right weight factor for being what you want. Okay? Okay, so we do have this simple thing. However, what this simple thing proves, certainly, is that the range of the map E is an invariant subspace for the representation. Okay, because you see, I mean, if you take the range of the map E, and if you act by the representation, you will still get something which is in the range of the map E. Okay, this factor of G1 alpha has nothing to do with that. Okay, you could absorb it in the test function. Okay, so now what we have an invariant subspace, and the theorem is the following: is that so let now H be the co-kernel, be the quotient, if you want, be the quotient. I am not saying the orthogonal. I am taking the quotient because, as I was saying, you know, these actions are not unitary. Okay, so we have to take quotient spaces. So with the quotient of L2 delta of CK by L2 delta of X. Okay? And let us decompose this Hilbert space H as a direct sum of sectors according to the Grossen characters, so H sub chi, where chi is a character of the compact group K. Remember that the ideal class group had a sort of innocent part, namely it was equal to a product of a compact group by, let us say, R plus star if we deal with number fields. Okay, so I am talking about this compact group, and when I take a character of K, I can extend it to a character of CK, which is 1 on R plus star. So this is what I will very often do. Okay? So let's decompose the Hilbert space into a sum over the characters of K, which are called Grossen characters, by the rule, if you want, the usual rule, which is that H sub chi is the space of vectors psi, such that when I act by the quotient representation, which I will denote by W, W of J of psi is equal to the character, chi of G, times psi, okay, for any G belonging to K. Now remember, K is a compact group. On K, the module is equal to 1. So the action of the subgroup K is unitary. Okay, so there is absolutely no problem when you write down the decomposition. This action is unitary. And this decomposition is just completely ordinary things that you just decompose into sectors. Okay, you just want to consider one character at a time. I mean, you could also speak of all of them at once, but I mean, this is nothing. Now the theorem is the following, is that if now you consider the spectrum of the corresponding representation in the space H sub chi, it will deliver for you exactly the zeros of the L function with Grossen character chi. Okay, and those which are on the critical line.
When you describe H of X, what is W?
A W is a quotient representation. Namely W, let H be the quotient and W the quotient representation. Okay, you see, because you divide by an invariant subspace, so there is a corresponding quotient representation of V. Of V. Of V, okay? Of the representation V. Of the representation V. So remember that we knew that V was not unitary but almost unitary. And the proof that the spectrum of V was unitary continues to hold for W, even though W is a quotient representation. Because the same inequality holds for the quotient representation. You see, the representation V is very trivial. It's a regular one. W is much less trivial because it's a quotient. But the same inequality which was holding true for V continues to hold for W just by the definition of the quotient norm. Okay? All right, so W is with unitary spectrum. That's true. And now the theorem, the statement, is that on H sub chi, okay, the operator, which is the generator of the representation, namely the operator D sub chi, equals limit when epsilon goes to 0 of W of e to the epsilon minus 1 over epsilon. This is what one calls the infinitesimal generator of the representation. Okay, so this operator is as spectrum, as discrete spectrum, and we can compute its spectrum exactly, and purely imaginary spectrum. So you see, it's purely imaginary because if it were a unitary representation, remember that you have to put a square root of -1 when you define the generator. I didn't want to put it, so I get purely imaginary spectrum. You see, when you define the Lie algebra of var, okay, normally you have to put an I normally in this formula. Wait, this theorem will be true for all values of delta, okay? And purely imaginary spectrum. Moreover, some number, which now has to be purely imaginary, so moreover, IS, if you want, belongs to the spectrum of d sub chi, if and only if, okay? So now, if and only if the following holds, if and only if the L function L of chi and 1/2 plus IS is equal to 0, and 1 plus delta over 2 is strictly bigger than the multiplicity of the 0. Okay? I mean, what I'm saying is that it occurs exactly as many times as the multiplicity of the zeros and the infimum with 1 plus delta over 2. Okay, so if you want, let me put this. Let me assume.
The multiplicity of 1 over 2 plus I.
Yes. Let me assume that delta is bigger than 1. Okay. Then what is true is that IS belongs to the spectrum if and only if the L function vanishes at the point. Okay. Moreover, the multiplicity, the spectral multiplicity. So that's true. But then the spectral multiplicity is given by the infimum of the multiplicity as a 0, and 1 plus delta over 2. That's strict. Okay? See, it is the multiplicity, the spectral multiplicity is the largest integer, which is strictly smaller than 1 plus delta over 2, and which is less than the multiplicity as a 0 of the L function. Okay? So let's stare a little bit at this theorem. Let us stare a little bit at this theorem. I mean, this theorem is not difficult. We shall see, and we shall see it's a preliminary result only. But it has a lot of convincing feature. To me, by far the most convincing feature is that I didn't have to define the L function or the Riemann zeta function in order to get all of its zeros. And I didn't have even to talk about analytic continuation. And if you look at the Riemann zeta function, you don't even have to mention complex numbers. I mean, except for this stupid I. But I mean, you can work with a real space. You see? I mean, you can work over real numbers with L2 over, because the Grossen character this time is trivial, and you can do everything real. So I mean, you reach, if you want, the zeros of the Riemann zeta function appearing spectrally without even having dirty ends. You see what I mean? And of course, that's an absolutely necessary condition. Okay, so this is the first remark. Now, the second remark is that when you look at these L functions with Grossen character, if you want, they depend very much, the function L of chi and S does depend upon the decomposition of the ideal class group Ck as a product of a compact group by R plus star. Because there are several ways by which you can map back R plus star in the ideal class group. So there is a normalization, but you can readily check that the change that you get in the L function when you change the normalization is by a shift in S. And that exactly the same change appears in the spectral interpretation. Okay, so I mean that's also very clear. Now it will be very important later also that we are extremely careful, if you want, in computing the trace. So I will immediately write a corollary of the theorem, which is the computation of the trace. And whereas here I was restricting myself to number fields, because I wanted to have the infinitesimal generator, so I wanted to have R plus star. Okay? When I write the computation of the trace, it will be valid for any global field, without any condition. So this is nice. Okay? Now, the computation of the trace is the following. You see, so it will be the spectral computation. Now we know what is the operator. We know what is the spectral multiplicity. So we know what is the trace. And we can write down the trace not on the generator, but on the representation itself. You see, I mean, when okay, I will do that just now. So I will stop here, but what I will do at just the beginning, I will not rewrite the theorem, but I will write the trace computation, okay? And this will be extremely important for later, because what we shall see then is another way to compute this trace, which is purely geometric, from the fact that we have a geometric realization, okay? So I'll stop here. Let me just, yeah, okay. Good. So it's a trace class operator, it has a trace, and the trace of W of H is computed by the following formula. By the way, in that you don't have to split the Hilbert space into the sum of the H sub chi, it will automatically be the case. So it's trace class on the Hilbert space H, which is L2 delta of Ck divided by L2 delta of X. Okay, and its trace can be computed, and trace of W of H is in fact equal to the sum, and the sum is extended over all Grossen character chi, and all S such that L of chi of 1/2 plus IS is equal to 0, okay, and with the rule of multiplicity which is given here, and then you just take the Fourier transform of H, which you evaluated at chi and S. Okay, and the Fourier transform of the function, or maybe let me put IS here. Okay, so the Fourier transform of H I define by H hat of chi and Z is equal to the integral over the delta group Ck of H of U times chi of U. I don't put a bar. Chi of U times absolute of U to the power Z, and then d star U. And notice that this formula is homogeneous because there is an appearance of the multiplicative R measure, d star G, here, and there is another appearance of the multiplicative R measure in the definition of the Fourier transform. So if you rescale both, they will rescale in the same way. Okay? So everything is sort of homogeneous. Now, because, you see, now, because we imposed the two auxiliary conditions on the Schwarz space, that the function vanishes at 0 and the function has an integral which is equal to 0, okay, in fact, when you compute the trace normally, you see, so if now you would compute formally the trace, not of W of H, but if you compute the trace of U of H now, okay, namely the action on L2 of X, right? Then you see that, let's do it formally. You see that it was an absorption spectrum, so there, you see, when you compute a trace on L2 of X, not on H, you have to use an exact sequence of spaces, which is that 0 goes to L2 delta of X, goes to L2 delta of Ck, goes to H, goes to 0. Okay? So when you compute the trace here, what can you say? You can say that the sum of the trace here and the trace here is equal to the trace here. But the trace here, this is white noise. This is just a regular representation. It's just given by the value of the function at 1. Okay? So what do you know? You know that the trace here is the opposite of the trace here. And this is our minus sign, which was missing in the previous discussion. Okay? And moreover, there is a coefficient, because remember that U of H is not equal to W, but there is this factor of j to the 1/2 in the formula. And if you use this factor of j to the 1/2, you'll find that it is a Fourier transform at 1/2 plus IS. Okay? And because of the two linear conditions that I have imposed, you'll find that you have to subtract H hat of 0 and H hat of 1. Okay, and this will correspond then exactly to the formula like in the Lefschetz formula, where you have the action on zero-dimensional cohomology plus the action on the two-dimensional cohomology minus the action on the one-dimensional cohomology. Okay? So let's keep this in mind. I mean, this corollary will be sort of obvious once we have the proof of the theorem. And let's begin the proof of the theorem. So as I said, you know, it was important that we could state the theorem without knowing what is an L function. But of course, to prove it, you have to know what is an L function. I mean, this is sort of obvious. Okay, so what are these L functions? They are the so-called AKL functions. And the AKL functions are, if you want, there are two definitions of L functions. There is a definition which uses a Galois group, which is the Artin L functions. And there is a definition which is using the Idel class group, and which are the AKL functions. And the fact that these two L functions are equal is exactly the content of the class field theory, of the reciprocity law, the Gauss reciprocity law. Okay? So AKL functions are associated to, sorry? Artin reciprocity. Yeah, okay. I mean, you know, originally it was Gauss, of course. I mean, then it exploded in many. Okay, so the AKL functions are associated to Rosen characters. So, I mean, they are associated, if you want, to a character of CK. And I will, you see, remember that CK was equal to K cross R plus star, let us say. And in fact, I mean, it's important to distinguish in the character two pieces. And I will write the character, if you want, in the form chi. Chi of G, I will write it always as chi 0 of G, where chi 0 is unitary character. And I will assume to be 1. I will assume that chi 0 restricted to R plus star is equal to 1. Okay, and then you multiply it by a character which is a character of R plus star, if you want, of the R plus star part, and which I will write G to the power, let me say Z, for instance. Okay? Or maybe I will write G to the power S. Okay. Now, this character is unitary if S is imaginary. So if S belongs to IR, then chi is unitary. So chi of G belongs to U1, if you want, which is included in C star. But if S does not belong to IR, well, this is called a quasi-character. So it's not unitary, but doesn't matter. Okay, and I mean, it's the size of this character is governed by the real part of S. Okay, so now the corresponding L function, L of chi and S, we shall write two formulas for it. The first formula will be a formula, if you want, which invokes only chi, and the second formula will be very reminiscent of what we know for the Riemann zeta function for the Euler product, and will invoke S. Okay. Now we need a little notion which is already appeared, which is the notion of ramification. So in other words, if we have such a Grossen character, chi, or chi 0, for that matter, it doesn't change the ramification. What we can do is we can decompose this character, we can lift it to the group of which Ck is a quotient, namely the Idels, divided by K cross. And the Idels, if you want, they are, in fact, the restricted product of the invertible elements of the group of GL1, if you want, of the local fields. And this product is taken with respect to the maximal compact subgroups, which are R star V, for almost all places. So if a group is of this form, when you consider a character of the group, you can always write chi as a product of local characters, chi sub V. And the ramification comes by looking at a place and by looking at chi sub V restricted to R star V. Okay, now it is clear that for almost all places, because we are dealing with a restricted product, the restriction of chi sub V to R star V has to be 1. Now when it is 1, it is called unramified. And if it's not 1, it's called ramified. Okay? So I mean, it's important because there is a finite set of places. So there exists a finite set P of places so that it is unramified. So that at this place it's ramified and elsewhere it's unramified. So if you want, now the L function is defined like this. L of chi 0 and S is equal to the product for the unramified places of 1 minus chi of pi sub V, the generator of the, I mean, they are unramified place and they are finite place, V finite. Okay? So you don't consider infinite place. Of 1 minus chi pi sub V inverse. Okay, so now when you compute, of course, chi of pi sub V with this formula, what you find is that it's equal to chi 0 of pi sub v times the norm of pi sub v to the power s, but this is equal to q sub v to the power minus s. So of course you come back to the ordinary formula. Okay, so that's the definition. This function makes sense whenever the real part of s is larger than 1. Okay, and let's see now how it appears. Okay, so the way it appears is from the work of Tate and Iwasawa, but as interpreted by André Weil. Okay, in I think a paper which was published in Bourbaki, and in which André Weil interpreted this work by means of homogeneous distributions on others. Okay, so it is interpreted like this. It's very simple. So you consider homogeneous distributions, and let me first discuss the local case and then the global case very briefly. So you see, you consider first the local case. So you consider a local field K. Okay. Now you say that the distribution D, so D is distribution on K, and by distribution on K I mean a linear form on Schwarz space, which is continuous for the norms defining Schwarz space topology. So a distribution on K is homogeneous of weight chi, sorry, where chi is a character of K star. So K star to C star, so quasi-character also if you want. So it's homogeneous of weight chi if and only if the following holds. If and only if when you apply the distribution D to the function f but shifted by A, what you get is chi of A inverse times f. Okay, so this is the value of the distribution on the function, and the shifted function is just f sub A of x is equal to f of ax. Okay? Now, we know plenty of examples of such distributions, homogeneous distributions, but I mean, in general, you can write them like this, that you just take the integral of the function f that you restrict to the multiplicative group. So the function f is a function on the additive group. Okay, so what you can do is you can define a distribution D by the following formula. D of f is equal to the integral over k star of f of A times chi of A times d star A. Okay, so d star A is the multiplicative armature on k cross. You can restrict the function here, and you will see immediately that that makes sense, provided the character chi, the quasi-character chi, has a real part of S which is positive. Okay, so that converges. The reason why it converges is that this will behave like some A to the power epsilon for A small, and this behaves like dA over absolute of A. Okay, but this integral is finite. Okay, so you see that you have no problem. So as soon as, if you want the real part of S for the character chi is strictly positive, this makes sense. And it is obvious, you know, that if I replace f by a shifted f, so let me put an x here, not an a. Okay. Okay, let me put the x here. Now, if you replace f by fa, okay, what you will get here is f of ax, and by putting y equals ax, okay, you'll pick up a chi of a inverse. Okay, I mean, just check me. The only thing that could go wrong in my proof essentially is that I make a mistake between chi of A and chi of A inverse. And this would be fatal. Then, because when I will compute the trace formula, it better be right. Okay? All right, so that's why I'm sort of over careful, you know, with these things. Okay. Now, so this is the definition of D of F. It's homogeneous of degree chi, I mean of weight chi. And now, you see, if you consider so this works in general for arbitrary local field. But if K is non-Archimedean, you can do a little bit better. If K is non-Archimedean, you see, eventually what you want to do is you want to apply these homogeneous distributions to the Schwarz space of the Adels. Now, as I told you, the Adels are an infinite tensor product. I mean, are an infinite product. So when you consider Schwarz space over the Adels, it is equal to an infinite tensor product according to the characteristic function of the maximal compact subring, 1RV, of the Schwarz spaces of the respective local fields. And when you consider the respective local fields, S of kv, what you find out is that if you want to have a distribution, to make an infinite tensor product of distributions, it will make sense provided for this distribution you have the normalization that this sub V, the local distribution, evaluated on the characteristic function of the maximal compact subring, better be 1. You see, because then you can make the infinite tensor product. Otherwise, you'll be in trouble. Okay, so this is the only thing you have to check, that when you will evaluate the local distribution of which you want to make infinite tensor product, when you evaluate them on RV, you get 1. Now, if K is non-Archimedean, you can do that trivially, because you can define a local distribution, which I will denote by delta prime sub V, and if you insist that I put a chi, I will put a chi, okay, which will be defined like this. So this evaluated on F will be equal to the integral, again, in the same way, over K star, if you want. But this will be K star V, because I'm this local thing, of what? Of the function F of X minus F of pi V inverse X, okay, d star X. Now observe one thing, which is that this function, because the function F is in Schwarz space, it is locally constant. Okay, so this function is 0 near the origin, because you see it's constant in the neighborhood of the origin, and when you shift it by this, you still get the function is 0. Now this function, so this integral makes perfectly good sense. I forgot to put the character, sorry. Chi of x, okay. So this integral makes perfectly good sense, because you see the only problem was with the neighborhood of 0 here. Okay, so now it's perfectly well defined. Function is compact support and so on. It has the right homogeneity because I have just added two things which have the same homogeneity degree. Okay, and moreover, when you compute it, you find two things. You find first of all that it satisfies this requirement, namely that if I take delta prime, see if you take delta prime, chi sub v of 1 RV, what will you find? You will find the integral here of the characteristic function of RV, so 1 RV. Now here you will find the characteristic function of 1 of pi v times RV. Okay? So the difference between the two is the characteristic function of R star v, the invertible elements. Okay? Now if you take invertible elements, and if the character is unramified, okay, that function will be 1 in this place, and what you will get is the integral of d star x. But when you take the R measure for the product of the things, of course the R measure will be such that it's a product of R measure, d star of xv if you want, and it will be normalized, of course, so that the integral of d star x of v is 1 on R star v. Okay? So you get this condition, so there is no problem. Moreover, you see, so it satisfies this condition, but it satisfies another condition, which is that you can compute this integral trivially by doing the change of variable here. And what do you get? You get that it is equal to 1 minus chi of pi sub v, okay, times, so you see I'm just making the trivial change of variables, and I don't get chi of pi v inverse because in the change of variables I have pi v which appears, not pi v inverse. Okay, so it's equal to 1 minus chi of pi sub v times the integral over k star v of f of x, chi of x, d star x. Okay, and I mean, this very simple fact is exactly the place where the L function appears. Okay, why? Because if you stare a little bit at this fact, and if you stare a little bit at this condition, what do you find out? You find out the following identity, you see, that on Adels now, there is a homogeneous distribution, which is obtained simply by taking the infinite tensor product of the homogeneous distribution delta prime chi sub v. Okay, so you have two ways of constructing an homogeneous distributions on the Adels. Okay, the first one is to take an infinite tensor product. You see, because, yes? Okay, why do you need this one, you mean? Yeah, you need this condition for the following reason, that when you take this infinite tensor product, it is with respect to the vector 1RV. What does it mean? It means that an element here, you see, it's given by some function, let f1 tensor, fv1, let us say, times fv2, okay, times fvn. Okay? But after finitely many places, you will everywhere have 1 RV. You see what I mean? So all the terms will be 1 RV. Now, if you take a linear form on that space, okay, which satisfies this condition, namely if you take dv1 tensor, dv2 tensor, and so on, okay, you see that when you will pair it, of course you will have the product of the pairings. But this product now will be 1 for almost all factors, so it will make perfectly good sense. Okay? Okay, so this is why you need this condition. And now what you can see is that there are two natural ways to get on the adels an homogeneous distribution of weight chi. Okay, where chi now is a Grossen character limit of the form chi 0 times absolute to the z, to the s, let us say. And let's assume that real of s is bigger than 1. So the first way does not depend on real of s bigger than 1. So the first way is the following, is to take that distribution, which I will denote by delta prime chi, and it is the infinite tensor product of what? It's infinite tensor product for V not in the ramified place, and for V finite, of the distribution which I denoted up there by delta prime of chi sub V and V. Okay? Which was normalized, remember. And then you just tensor it by a finite tensor product, which is tensor for V belong to P or V infinite. Okay, of the obvious distribution which I had written here. That one. Okay? That one let me denote it by delta sub V. Delta sub chi sub V. Okay? So this one is without a prime. So delta of chi V sub V. Okay? I hope this is clear. You see, I mean, this was the obvious definition, unnormalized. This is the slightly non-obvious definition, which is normalized. Okay? Now, there is another way, a second way. I mean, this is really Tate's thesis. And the second way is the following, is that you can now define another distribution, delta sub chi, by writing that delta sub chi applied to a function f is simply the integral over the dels, j, okay, of the function f restricted to the dels, times chi of u, times d star u, where d star u is the multiplicative R measure for the del. Multiplicative R measure on the dels. On J. And the fact that this converges is exactly the same fact that is telling you that the L functions or the zeta function makes sense for real of s bigger than 1. Okay? It's just a simple analysis of the convergence of this integral on an infinite tensor product. So you have these two ways. And immediately what you see is that, of course, they have to be proportional, because it's not difficult to see that you have uniqueness up to scale of homogeneous distributions. And the scaling factor, I mean, we know what it is because of this equality here. You see, when you write this equality, what do you have? The right-hand side here, this is delta V, okay? And the left-hand side here, okay, this is delta prime V, okay? So what do you know? You know that delta V is the inverse of this factor multiplied by delta prime V. And when you take the product of these inverses, you get exactly the L function. Okay, and this is the key. I mean, this is the key. So it's very, very simple. And so what do we get is that these two ways are comparable. And they are compared by the following equality. I mean, what is sort of curious is that the paper by André Weil stops short of the theorem that I wrote down. I mean, at the end, one can see that he sort of got distracted. I mean, the end of the paper is sort of written in a strange way. I don't know if you looked at the paper, but I mean, now what do we have? So we have an obvious equality, which is that delta sub chi is equal to L of chi and S. Remember, the S appears in the Grossen character. So chi is, so chi 0, sorry. L of chi 0 and S times, so remember that chi was chi 0 times absolute to the S times delta prime of chi. Now you see delta prime sub chi is very well behaved. It's an infinite tensor product. It's non-zero. It's a very natural and non-trivial distribution. So. But what you can see immediately is that, you know, if the L function vanishes, then something very interesting happens if it vanishes at some point. What happens exactly? Well, what happens is that if L vanishes at a point, then delta chi will vanish. And it will vanish for all f. What does it mean? It means that you will have that integral of f of u over the others, f of u, times chi of u, d star u, is equal to 0 for all f. Now I am cheating you here, because the interesting zeros, of course, are not occurring for real of s bigger than 1. So you have to do a little bit of something, okay, in order to make this thing nice. But what you can see with plain eyes is the following, is that now you can rewrite this integral, okay, provided we have done this little work, and we shall rewrite this integral as follows. It will just be what? You see, j is equal to, j modulo k cross is equal to ck. So this integral we can rewrite as integral of E of f, namely the sum of f of q times u, for q belonging to k cross, okay, multiplied by absolute of u to the 1/2, okay, chi 0 of u, okay, absolute of u to the s, minus 1/2, because I have put in the u to the 1/2 and I have subtracted it here. And now I put this star u, but now this star u is no longer the R measure on j, but it is R measure on ck. Okay? So let's remember. So in fact, what this is telling us is that for a certain pairing between Hilbert spaces, we have the orthogonality between the range of the map E, because this is just E of f. Okay? So we have the orthogonality between the range of the map E and the function, which is given by absolute of u to the s minus 1/2. Okay? And this will be the key. Okay? Namely, we shall compute, if you want, when I will compute the co-kernel, I will compute it by functional analysis, by computing the orthogonal, and this will be the key. I mean, this is just a starting point, of course, because you have a lot more to do. This will tell you that certain things are orthogonal. But then the difficulty will be to prove that nothing else is orthogonal. Okay? And this will be the real difficulty. But there will be a very easy part, which is that one. Okay, so this is the starting point. And so the starting point can be summarized by this proportionality equality here between delta chi and delta and the other one. Now the second point, and this is really also an absolute key, which shows that somehow in the Tate thesis this space X was present implicitly. I mean, he didn't spell it out, but it was obviously there. So let me tell you the key point now. So the key, the real key is the following, is that one has the following formula, which is that E of the Fourier transform of f evaluated at x is equal to E of f evaluated at x inverse for any f belonging to the Schwarz space with the condition 0. Okay, so this is a key. And how is it proven? I mean, of course, we know this is a functional equation, but this is a Poisson. And Poisson, let me remind you what is a Poisson. It is the fact that if you take a subgroup gamma of an abelian group A, say a discrete subgroup of a locally compact abelian group A, you always have the following equality, which is that covolume of gamma for the additive R measure times the sum of the value of a function on points of gamma. That's always equal to the sum of the value of the function Fourier transform on gamma at, gamma tilde, where gamma tilde belongs to the dual group, orthogonal of gamma. Okay? So this equality is just the simplest instance of a trace formula. Okay? I mean, you just compute the trace of the operator, which is an integral operator, in the space of periodic functions, and you find this equality. Now, this equality, you see, let me explain now a very important point here, which is that how do you apply it? You apply it because you have Fourier transform for adults, and Fourier transform for adults is defined by f hat of x. You take a basic character, so you take integral of a certain basic character alpha, evaluated on x, y, f of y, dy. Now in this, a lot of things are present. There is a basic character alpha, so alpha is just a character of the adults okay, but which vanishes, which is equal to 1, if you want, on K. Remember that K was a co-compact discrete subgroup of A. So in particular, there are characters which vanish on K and which are non-trivial, so different from 1. Now, what one can prove, requires a little bit of care, is that if you take such a character, the orthogonal of K is K itself. Okay? Namely, then K orthogonal, the orthogonal of K as a lattice is equal to K, and you can apply Poisson. Okay? But the fantastic thing, which is really very non-trivial, I mean, in this thing, is that, you see, when you consider Poisson applied to the discrete group gamma, which is X times K. Okay? Now, this is still discrete, because you have multiplied by X. Now, the thing which is really absolutely amazing is that X times K is equal to 0 union xk star. Okay? I mean, you will tell me, this is very trivial. You see why? Because X times K is, of course, the union of X times 0 union X multiplied by a non-zero element of K. But this is extremely non-trivial because xk star is precisely the orbit of X under the action of GL1 of K. Okay? So in other words, this fact, which is extremely non-trivial, that every element non-zero in a field is actually in the corresponding group of invertible elements. Okay? What does it tell us? It tells us that when we multiply the additive subgroup K by X. In fact, up to the point 0, we get the same thing as the orbit of X by the action of GL1 of K. Okay? And what does it mean? It means that when we apply the summation, the sort of Poincaré series, for the action of the group GL1, namely when we apply the map E, which is E of F, I remind you, E of F of X is equal to X to the 1/2 times the sum for Q belong to K star of F of Qx. Okay? In fact, that's the same thing as the sum of the value of the function on the subgroup gamma, where gamma is X times K, except for the point 0, but remember that F was vanishing at 0. Okay? Now this is it looks very trivial, but it's a very non-trivial fact because this is a place where, in fact, the quotient of the Adel by the action of GL1 of K is implicitly entering. Okay? Okay, and obviously by Poisson, when you apply Poisson, you get this equality here. You see what happens is that the covolume, when you take the group, the covolume will be given by absolute of X times, that's all, absolute of X. And then you will have the sum of the value of F of Qx, okay, for Q belonging to K star. I don't care for 0 because of what I said, the function vanishes. And this will be equal to the sum of the Fourier transform evaluated at, again, Qx, okay? And I can put for Q different from 0 because remember that the integral of the function was vanishing. So the Fourier transform vanishes at 0. Okay? So you have this formula. Now if you have this formula, well, now essentially you are in infinitely better shape because what do you see? You see that now this integral, okay, once it is written in that way, okay, makes sense for any value of S. And this is the proof, if you want, of the functional equation and of the analytic continuation in Thay's thesis. But what it tells you really is that without any difficulty, somehow, I mean, of course, you have to prove something. You have to prove, which I didn't prove, but I mean, you have to show that when you look at the function E of F, you see, the Schwartz space is stable under Fourier. And the two conditions, the two linear conditions that I put are stable by Fourier. So if you want to prove that the function E of F is well behaved for large X, okay, I mean, what you find out is that the behavior for small x, for E of F of X, you will know it, provided you know the behavior for large X, just by applying this formula, because you can replace F by F hat. Okay? Now, the behavior of E of F for large X is not difficult to control. I will do it if necessary, but I mean, it's really not difficult to control. And what you find directly by direct computation is that for a function in Schwarz space, E of f of x is in fact of exponential decay. Namely, E of f of x is less than a constant times absolute of x to any power, negative power minus a, okay, for a function in Schwarz space, okay? And that's because we are working with a multiplicative group. That means exponential decay. Now, you can do the same thing with f hat, applying to f hat, the same reasoning. And of course, you see that the function is also decaying very fast near 0. For that, it's crucial that you have these two linear conditions, because it's crucial that you apply Poisson. Now, what we shall see later, okay, this is very rough because it's only qualitative, okay? So this is extremely rough. What we shall see much later is that in order to prove veil positivity by inequality operators, what will be crucial is that we notice already from the formula for E of f, for this formula, we notice that if the function f would be such that f of x is equal to 0 for modulus of x less than a constant a, okay, then the same property holds for E of f. Why? Because the modulus of q is always equal to 1 for elements of the field, okay, because they preserve the additive R measure, okay. So this is in fact the content of the vanishing part of the Riemann-Roch theorem. Okay, when you look at the proof of the Riemann-Roch theorem for fields of finite characteristic, this is exactly the content. And the proof of the Riemann-Roch theorem itself is in fact the Poisson formula. Okay? And when we shall combine the two, what we shall prove is that a certain projection is smaller than another one. And this will give us the key to the veil positivity. Of course, assuming the trace formula. Okay? But, I mean, keep that in mind. So somehow, these simple facts that I am proving for the proof of the theorem will be much more refined later. Okay? I mean, this is qualitative. What I am telling you here, and is simply that, okay, by just playing with that, we get immediately that all the formulas that I had written, this proportionality, for instance, which was only valid for real of s bigger than 1, because the two sides are analytic, continue to be valid now, let us say for real of s positive. I don't care for other values. Okay? I remind you that when I had defined this delta prime chi, I was assuming simply that real of s is positive. Okay? I don't care for, because if you take values where not the real of s is positive, you have poles. Okay? And I don't want to encounter this. So we still have this equality for any value of real of s which is positive just by applying the fact that the function that when I write the distribution delta sub chi, I will now rewrite it, and instead of writing it like this, I will write it like that, but it's equal to integral of E of f, and it's an integral over ck, E of f of a, let us say, times chi 0 of a, times a to the power s minus 1 half. D star A, where D star A is the R measure. Okay, so now we can summarize everything which was said so far by the fact that this makes sense for real of s positive. Okay, in fact, it makes sense for any s, but both make sense for real of s positive. And we have the equality that delta sub chi is equal to L of chi 0 and s times delta prime sub chi. And this is true for any s with real of s positive. Okay, so let's forget about the rest. Of course, we shall use this equality many times. I mean, this key equality many times further, but we can forget about the rest for the proof of the theorem. So now let's prove the theorem. As I said, there is a part which is very easy. Yes? Sorry? So the theorem that I had written here. Theorem that was erased, about the spectral interpretation. Okay? So I absolutely want to finish that proof. Okay, so let me prove it. So you see, what do we have? We are looking for the inclusion of L2 delta of x into, by this map E, into L2 delta of ck. Okay? And we want to understand the co-kernel. Now, if you want to understand the co-kernel of the map, the best way with Hilbert spaces is to look at the dual space, okay, and dualize the problem by usual thing. So but for this, it would be crazy to look at the orthogonal in L2 delta because that's not a unitary representation. So rather than doing that, you use a pairing, and that pairing is unitarily invariant. And it is a pairing like between Sobolev space, namely it's a pairing between L2 delta and L2 minus delta. Okay? You see, it's exactly like for Sobolev space. Okay? Now, if you look at that, what you will find out is that if you look at L2 delta chi, okay, which is the space of vectors xi, which satisfies that V of g xi is equal to chi of g, chi0 of g, times xi for any g belonging to k. Okay, when you look at this subspace, what you will find is that the dual space is L2 minus delta chi bar. So, and this pairing, I want it to be bilinear. Okay, I want to be very careful on that. I don't want it to be skew linear because otherwise I will be worried by chi bar and so on. I want it to be bilinear. In other words, it's given by integral of psi of g, eta, not eta bar, eta of g times d star g. And the integral is on ck. And that's, of course, invariant, okay, under the unitary representation, v of g. There is no delta here. See, it's very important that when you compute the orthogonal, you don't use delta. Okay, you pass to the dual space, which is like a Sobolev space, but with the opposite exponent. All right, so this space L2 minus delta chi bar is a set of xi now, which are such that if I look at xi of gx, that's equal to chi0 of g times xi of x. Okay, for any g belonging to k. All right, and the xi are just functions. The xi's are just functions. Are functions on ck. Okay, so I mean, we know these functions. They are all of the form. So any such xi can be written as xi of g is equal to chi0 of g times psi of absolute of g. Okay? Any such function is of this form because we know how it varies by ck1. And remember that what is by k. What is remaining if we mod out by k is just the absolute value. Okay, so any function is of this form. Okay, so now the lemma, which is the key lemma, is the following. Okay, so now the function psi, so lemma is that psi belongs to the orthogonal. I'm managing not very well with the chalk, but belongs to the orthogonal of L2 delta of x. Okay, if and only if the following holds. If and only if the product of the L function L of chi0 of s times the distribution psi Fourier transform at s is equal to 0. You see? Okay, so what I am saying here is the following. This is the main lemma. Now, you see the function psi is a function on positive real numbers. Okay? And the function psi satisfies that it belongs to L2 minus delta, namely that you have integral of psi of u times 1 plus u, log u, square to the power minus delta over 2, d star u is finite. Now let's put u equals e to the s, and let's pass to an additive variable. Okay? This function is such that it is L2 for some weight. What does it mean on the Fourier transform? It means that the Fourier transform is a distribution, okay, with some order, which is automatically a tempered distribution, because it's Fourier transform of this. Okay? And what I am saying now is that by inspection, but this requires a lot of work somehow, what you find out is that the Fourier transform of this distribution, psi hat, how do I Fourier transform? I should say Mellin transform, but I mean I can say Fourier transform. So psi hat of s is just equal to the integral of psi of u, absolute of u to the is d star u. Okay, this is the Fourier transform. You can call it a Mellin transform if you want. I call it Fourier transform. Okay. Now, so the statement is that you belong to the orthogonal if and only if this product vanishes. Okay. Now, this is an equation in distribution theory, and because the L function is a tempered function on the critical line, okay, which doesn't grow faster than a polynomial, this equation is well defined. And moreover, the solution to these equations are sums of Dirac distributions carried by the zeros of L and their derivatives, but not exceeding the multiplicity of the zero. Okay? So let me prove the lemma. So once you have the lemma, you just apply the results from distribution theory. That certain equations in distribution theory only have delta functions as solutions and their derivatives, and you get the answer. But how do you derive this? I mean, this requires some care. And it's derived like this. So essentially, you see what is going on is that on the function psi, it is really the convolution operator by the Fourier transform of the L function. You take the L function on the critical line. It has tempered growth. This is well known. And then you take its Fourier transform as a convolution operator, and its product by psi is actually 0. So let me just mention one word how this is proved. This is done in the paper, okay, in detail. So how this is proven? I mean, what you do for that, I just want to mention one equality, and then I stop. So, I mean, it does require some care, really, because what you do is you write down, you see, you write down this equality, of course, this is a key equality, but you apply it to test functions f, and these test functions, you take them of the following form. You take test functions of the form f is a product, tensor product, of functions which are the 1 Rv, for v does not belong to P and v finite. Okay? Then you tensor by functions which are the Grossen character but opposite at finite ramified place, so v ramified. Okay? And then you tensor for infinite place by, now you choose your test function, I mean f0 here. Okay, and you tensor it also by the Grossen character at the infinite places, but complex conjugate. Now you choose the function f0 in such a way that if you want, you have several infinite places, kv for v infinite, and you choose the function f0 so that when you write down the e, okay, the average, well, you find a function which is an arbitrary test function b of the modulus, b of u. Okay, and from that you conclude using this equality over there that you get integral of L of chi0 of s times Fourier transform of psi at s times the function b of x times absolute of x to the 1/2 plus is d star x ds equals 0 for any b. And from that you conclude that the Fourier transform, you see, because this is Fourier transform in B, so you conclude that this distribution multiplied by any other such function is 0, so it has to vanish. Okay? And then you get the answer. But I mean, it's a little bit, there is a little bit of a detour. I mean, there is something which is obvious, which is that if you have a 0, you are in the orthogonal. But it takes some work to show the converse. Okay? So, and this is how you get then the, I mean, okay, but as I said, this is only a preparation. Okay, this gives us a sort of moral security that the zeros are there in the orthogonal complement, I mean in the cokernel.